Please go ahead and add 2 so that this equation is a balanced equation. So, in addition to acids reacting with solid oxides, hydroxides, carbonates, and bicarbonates by a double replacement reaction, acids also they can react with metals, certain metals, not all metals though. And the reaction is going to be a redox reaction. So this is the table of the activity of metals. We have some metals that they are very reactive in presence of water, like for example sodium, potassium, sodium, calcium. These metals they react vigorously with water. Now, the copper, mercury, silver, platinum, and gold, these are non-reactive in presence of an acid. So copper has no reaction when you put it in acid. Same thing for mercury, silver, platinum, and gold. These they do not react with acid. The metals that react with acids are magnesium. Magnesium react vigorously with acid. So if you can see in this table over here, as we go up in there, the reactivity is going to increase. So I'm expecting magnesium to react vigorously with the acid, like for example HCl solution. Aluminum is also going to react vigorously. Zinc is going to be kind of like you do have zinc is there. It's kind of like moderate. Chromium is moderate. Iron is also a moderate reaction. And again, copper has no reaction at all. So if you take a beaker and you dissolve a piece of copper in HCl, you're not going to see any reaction. You see a reaction when the piece of metal starts dissolving. So with iron and HCl, you're going to see that the iron is going to start to dissolve, but the process is going to be really, really slow. So you would say that this one is a slow reaction with iron. Iron does not dissolve in HCl. If you put a piece of zinc in there with HCl, it's going to start forming bubbles. Those bubbles are hydrogen gas. And it is going to be a moderate reaction. It's going to take a while until it dissolves in the acid, depending on how big the zinc is and how concentrated the HCl is. The more concentrated the HCl, the faster is the reaction with the zinc, so that the zinc metal will dissolve. Now, with the magnesium, it's going to be a vigorous reaction. So, if you put a piece of magnesium in there, concentration is concentrated HCl, it's going to take like maybe 30 seconds or so, and then you're going to see a lot of hydrogen bubbles forming, and then the magnesium metal is going to disappear. So, we would say that this is a vigorous reaction. So, to know how vigorous it is, you need to check and see now, how much gas are you liberating? How much hydrogen gas are you liberating? So zinc going from 0 to positive 2 is going to be oxidized. So zinc over here is oxidized. And then hydrogen is going from positive 1 to 0. So hydrogen in this case is going to be reduced. Hydrogen is going to gain. So it's going to be reduced. So I would say that HCl in this case, definitely, it's going to be the oxidizing agent, and zinc is going to be the reducing agent. Now, with respect to the spectator ion, let's draw the total ionic equation. So that is going to be zinc plus 2H plus aqueous plus 2Cl minus aqueous, and that's going to give me zinc 2 plus aqueous plus 2Cl minus Cl minus aqueous. So it seems that the chlorine is going to be my spectator ion. And then hydrogen gas. So the chlorine in there is the same ion, it's a common ion. So it seems that the Cl minus is going to be my spectator ion. And that is going to leave me with the net ionic equation of zinc solid plus 2H plus aqueous. That is going to give me zinc 2 plus aqueous plus hydrogen gas. Bases. So bases, they do feel soapy. They are slippery to the touch. And a basic solution contains an OH minus ions. Basic solution have a pH greater than 7. And normally we test the pH by the litmus paper. A litmus paper is a pH paper, and a pH paper is a paper that changes color based on the solution that it is in. So if you put the pH paper in an acidic solution, then it's going to turn pink in color, and this is the acidic version of the colors in there. So the red, the more red, the more acidic it is, and the greener it is, the more it's closer to the neutral. So these are the variations of the colors of the acid. If you put the litmus paper in a basic solution, then it's going to turn into a blue color. So the darker the blue color, the more alkaline, which means that the pH is between 10 and 12. As you approach 14, the color of the pH paper will become kind of like a purple, a dark purple color. It's going to be a very, very dark purple color. This indicates a high pH, meaning a high alkaline solution. Bases, they do react with acids. This is what we said earlier. And we said that bases, they take the acidic hydrogen. Always, bases take the acidic hydrogen. And the product is always the conjugate acid and the conjugate base. Conjugate acids, conjugate bases. And they're normally the conjugate base, we call it a salt. So you do have conjugate acid, conjugate base. Okay, so you're going to form salt plus water. The salt is normally the conjugate base. An example, we did this earlier. So OH minus is an indication of a base. So that is going to be my base over there. The hydrogen is the acid. So here I'm reacting the acid with the base. HCl is hydrochloric acid. So the base is going to come from the oxygen. It's going to come and take the hydrogen from the acid. So your product is going to be water. So we said that the base turns into a conjugate acid, and the leftover of the acid will turn into a conjugate base. Conjugate bases are almost, they are called, or always, they are called salt. So bases, they do react with fats, they do react with oils, and they do convert them into smaller and soluble molecules. In the second part of the course, we will talk about fats, we will talk about oil, and we will talk about their hydrolysis and presence of a basic medium to change into smaller molecules. Bases are used in everyday life, and most household cleaning reagents, these are made up of weak bases and weak acids, not strong bases, of course. So they are weak bases and weak acids. This is most cleaning products. So when we use lye in draining in drain to clean it, this is a strong base. If you use ammonia, this is a liquid household cleaner. It's not harsh. It is ammonia is a weak base. It's not a very strong base, so this is why we can use it as a cleaning agent as well. Weak acids, like for example soda. In soda, they do put phosphoric acid, H3PO4. It is edible. It's in a very low concentration, but phosphoric acid is so bad for the bones. So this is why it is not recommended to consume any of these carbonated drinks. So whenever you are reacting, let's go up. Whenever you're reacting an acid and a base, we call this a neutralization reaction because the base is reacting with the acid, and you're going to get the conjugate acid and the conjugate base. So it is basically a neutralization reaction. And a neutralization reaction is a reaction where the components of the products are neither basic nor acidic. So notice over here, I'm forming water, I'm forming NaCl. So I'm not forming H plus or OH minus in this case, so that the reaction will be favored more towards the acid or base. No, I'm forming water, which is kind of neutral. So that's why I call this a neutralization reaction. So let's have a couple of examples of a neutralization reaction. So a neutralization reaction produces in the product water, because you're going to end up getting a neutral solution. So you're not going to end up getting an H plus or an OH minus. So let's have an example over here. We're starting with a base, which is OH minus. So we agreed that whenever you see an OH, this is a base. hydrogen, a compound starts with a hydrogen, this is going to be an acid, and just apply the rule that bases take acidic hydrogens. And when they do, you're going to end up getting water. Water is a liquid. Water, when it's dissolved in the solution, it's called it is liquid, not aqueous, it's liquid. And then the leftover from the base is the sodium. The leftover from the acid is the NO3. So you're going to get salt. So you're going to get water in salt. And this is the definition for a neutralization reaction. Neutralization reaction always has a product that is water and salt. The water is going to be my conjugate acid, and the salt is going to be my conjugate base. This, if I want to name it, this is called sodium nitrate. Okay, this is another example, sodium hydroxide and H2SO4, sulfuric acid. So when I react this base, so sodium hydroxide is what? It's a base, and the sulfuric acid is my actual acid. So that is going to be my base. That is going to be my acid. So I'm going to end up getting my conjugate acid and my conjugate base. My conjugate acid is going to be water liquid. So that's going to be conjugate acid. The moment I get water to be my product, then this is considered to be a neutralization reaction. And then I'm going to get my salt, which is sodium sulfate. Okay, this is going to be my conjugate base. It's a sodium sulfate. So at room temperature, salts are crystalline. These are ionic compounds, and they contain what? They contain a positive cation and a negative anion. So if I look at the sodium sulfate, sodium is a plus a charge, and the sulfate is a 2 minus. So this is why I cross these charges, and then my formula is Na2SO4. So always salts are made up of two parts, a cationic part and an ionic part, an ionic part. And an ionic part and the cationic part, they are basically connected to each other by an ionic bond. So the type of bond between them is an ionic bond. So for example, sodium chloride. So if I give you a salt and I tell you, okay, give me the acids that resulted for this salt to form. Because whenever you have a salt, the salt comes from what? Comes from a reaction from the acid and the base. So always the cation is coming from the base and the anion is coming from the acid. Okay, so let's keep this. The cation is from the base, and the base here is the sodium hydroxide, and the anion is the Cl minus that is coming from, so the Cl minus anion that is coming from, just get any acid that has a Cl, so it's coming from HCl. Okay, let's have another example, sodium nitrate. So we agreed that the cation, which is the Na plus, is coming from the base, and since I'm using a base, then the only base that it's easy to predict is the sodium hydroxide, right? Because it does have an OH minus in there. So always cations, they come from the base. So this is the sodium chloride. This one comes from the base, and the anion comes from the acid. Just to choose any acid that has a chlorine. So take your anion, stick a hydrogen to it, and take your cation, stick an OH to it. Okay, so that's going to be sodium hydroxide. And then this one over here, hydrogen nitric acid. Here you go. So that is going to come from nitric acid. No, actually, here you go. The anion NO3, since the nitric acid is already there. So the anion NO3 negative, this comes from the HNO3. As we said, so you take your anion and you stick a hydrogen to it, you take your cation and you stick an OH to it. So the sodium cation, that comes from the NaOH base, and the sulfate anion, That one comes from, make sure that the hydrogen that you are going to choose here, because you're sticking a hydrogen, right? So it needs to balance the SO4 to a negative. I know that the hydrogen is one positive, so it needs to be two hydrogens there. So it's coming from H2SO4 acid. Okay. Normally the cations. Okay. Normally the cations are mostly metals. Now sometimes cations are NH4 plus. So they come from NH4 plus in there. So this is an actual polyatomic cation. So if this is the case, then again, cations always come from a base, so stick just an OH to it. And now the base for this cation is ammonium hydroxide, NH4OH. Okay. Um, the anion of the salt can be any negative ion except OH minus. So please pay attention to this one because the anion of the salt comes from the acid. It cannot be an OH minus. The cation from the salt, it comes from a base, so it cannot be an H plus. The salt hydrate. So to have a hydrate in there, to define a hydrate, it's an actual salt that contain X molecules of water in its crystalline lattice. And these molecules of water, we call them water of hydration. So these actually water molecules that surround the salt. So we call this a hydrated salt, a hydrated salt. And to name those hydrates, you start by naming the compound. So this is going to be calcium sulfate. And then how many water molecules do you have? This is one water, so it's going to be monohydrate. So the end is going to be hydrate. This is 10 water, it's going to be decahydrate. 12 is a dough, so it's going to be dough deca. So deca is 10, dough is 2, so it's going to be 12. So dough decahydrate. And 5 is penta, so it's going to be pentahydrate.